Deploying a functional application for a small group of users is a solved problem. The challenge changes entirely when traffic scales to millions of simultaneous requests, requiring an architecture that doesn't buckle under the load. Traditional, localized servers operate within rigid hardware limits. When faced with exponential global traffic spikes, these physical machines hit a ceiling where CPU and memory are exhausted, leading to system failure. AWS mitigates these hardware limits through a global infrastructure that distributes the load. By utilizing specific geographic regions, such as AP North-1, developers can host their applications closer to users while leveraging multiple data centers to handle surges. Within this infrastructure, the choice of storage affects long-term stability. While the EC2 Instant Store offers high-speed ephemeral storage, it is tied to the life of the host. For persistence, EBS elastic volumes allow for resizing and a performance tuning without downtime. However, for those aiming to maximize pure performance, RAID 1 is generally avoided due to the overhead of mirroring. As the system grows, the database responsibility model defines the split in labor. AWS handles the replication, maintenance, and basic scaling of the underlying engine, but the customer remains responsible for throughput planning and data security. Successful scaling moves beyond simply buying more powerful hardware. It requires a transition into a distributed, shared responsibility architecture where the provider and the customer manage different layers of the stack. Maintaining a fleet of traditional servers often results in a wasted resource bottleneck. Financial inefficiency grows whenever servers sit idle, consuming budget while waiting for traffic that hasn't arrived yet. Lambda removes server management. Compute power is allocated strictly per invocation, with environment variables passing parameters as functions spin up. CloudWatch alarms track health and usage metrics, providing a continuous monitoring loop to alert administrators if functions fail or exceed performance thresholds. For applications that require more traditional hosting, Elastic Beanstalk simplifies the process by managing the web server or worker tiers. It automates the provisioning, load balancing, and scaling, allowing developers to focus on code rather than the underlying instances. Managing these configurations manually is a recipe for inconsistency. To solve this, developers use AWS CloudFormation to treat their entire infrastructure as code, automating the deployment of complex resource stacks. A CloudFormation template is built from specific structural blocks, parameters for user inputs, mappings for conditional logic, and metadata for additional resource information. Notably, the CloudFormation specification does not include a settings section, relying instead on these defined blocks to build the stack. Defining infrastructure through these templates eliminates manual configuration errors. It allows a developer to deploy and replicate entire architectures across different regions with the same consistency as a software update. With compute scaling handled, the next bottleneck is information velocity. Modern applications generate data at a speed that can overwhelm the write capacity of standard relational databases. Kinesis data services provide a real-time buffer for this influx. Kinesis Data Analytics allows for immediate SQL-based processing on the stream, while Kinesis Data Firehose handles the delivery of that data to durable storage. These streams often lead to Amazon Redshift, a data warehouse designed for petabyte-scale OLAP workloads. It sorts data into columns for complex queries. For cryptographically verifiable histories, Amazon QLDB provides an immutable ledger, ensuring every tracked change cannot be altered or deleted. Even with these high-speed systems, relational data relies on full ACID compliance. Atomicity, consistency, isolation, and durability remain the standard for ensuring that every transaction is reliable and the data remains uncorrupted. At cloud scale, data is a continuously flowing system. It is routed, processed, and stored in real time to allow for immediate action rather than sitting as a static archive. Distributing an application globally increases the potential for security vulnerabilities. Without automated, stringent access controls, the speed of the cloud becomes a liability. Securing this environment requires moving away from permanent credentials. While static access keys are a common entry point for attackers, the use of temporary IAM roles for application access ensures that permissions are granted only when needed and expire shortly after. This diagram illustrates envelope encryption. The data is encrypted with a data key, which is then itself encrypted by a customer master key managed within AWS KMS. This creates a two-tiered defense that ensures even if the encrypted data is intercepted, it remains protected. At the network level, security groups act as stateful firewalls for individual EC2 instances. Because they are stateful, any traffic allowed into the instance is automatically allowed back out, simplifying the management of common web traffic. For broader network control, a NAT gateway allows instances in a private subnet to reach the internet for updates without allowing the internet to reach them. This sits alongside NACLs, which provide stateless, subnet-level boundaries to control the flow of traffic across the entire network. Security in the cloud is defined by layers. By replacing static passwords with automated cryptographic access and multi-tiered networking, the perimeter remains secure even as the infrastructure expands. The final step is managing the transition from a developer's workstation to a live production environment. The ultimate goal is a truly seamless delivery process that doesn't disrupt the experience for millions of active users. The build phase of the release lifecycle is where this begins. It involves retrieving the source code, compiling the application, and running automated tests. This phase is distinct from the final deployment, focusing purely on preparing and validating the code. Stages are connected by artifacts like compiled binaries, ensuring the exact tested code reaches the user. AWS Code Deploy uses these with an app spec file for deployment, handling in-place updates or blue-green strategies that shift traffic to a new environment to verify stability. AWS step functions can orchestrate this entire lifecycle. By managing the logic between different services, step functions reduce the need for manual oversight, allowing the pipeline to move continuously from a local code commit all the way to a live production deployment with high velocity and safety. Integrating these services shifts the focus from local code development to the architecture of automated pipelines. This approach enables the creation of systems that deploy updates continuously and scale dynamically to handle massive, unpredictable traffic spikes.